Okay, time for the final segment, transitioning from Pythagorean theorem to trigonometry. I'm just going to focus on square roots and calculator for this one. So earlier we saw, well, let's actually recreate it. Okay, 30, 60, 90 triangle. Do you know that? Try to write it out right now on your own. Okay, and then we had an interesting tangent relationship. So try this here. And I've got my 30 opposite the short side, 60 opposite the longer of the two sides. And then I pick opposite the 30 as 1. I remember this is 2, and then this is square root of 3. Now we have the tangent of 30 here. Tangent is opposite over adjacent. And again, how do I know that? I know that from my SOHCAHTOA acronym. And this will give me 1 over the square root of 3, opposite over the adjacent. Okay, but you may see that written differently. And the reason why is because, so I'm going to check what you would have memorized here. And then so you could see it like this. So if you have 1 over the square root of 3, it's called rationalizing the denominator. Okay, that's not meant to be a negative, it's meant to be a whole fraction bar. So I take root 3, basically you can multiply by 1, right? And the key here is you multiply by root 3 over root 3. And what do you end up with? Well, if I look at the numerator, 1 times root 3 is square root of 3, but the denominator here, root 3 times root 3, is just 3. So 1 over root 3 and root 3 over 3 are equivalent, okay? And this is called rationalizing the denominator. The name doesn't really matter. No, the reality is that it's usually not considered simplified to have square roots in the denominator. In this particular case, you may see it both ways. It's important for you to know that they're equivalent, because you might think, well, I got 1 over root 3, but the answer says root 3 over 3, so I guess I'm wrong. Now, actually, you're right. This is just considered, it's considered simplified by rationalizing the denominator. Because it doesn't really involve like any cancellation, it's not really better. For me, either one is fine of these, but you need to know both. Okay. What else do you have with square roots? And if I may show you, like I want to show you one where this might be a little more interesting. How about this one? What if we try to simplify, how about root 2, sorry, the root's got to be in the denominator for us to simplify. 2 over the square root of 2, okay? And so the idea is we use this same approach, okay? So to rationalize the denominator means what you want to do is you want to get rid of the square root in the denominator. So you say, well, what do I multiply by? Multiply by, the norm is multiplied by itself, square root of 2. Right, I'm multiplying by 1, so it's not changing anything. But look what happens. This is kind of fascinating. 2 times root 2 is just 2 root 2 over what? Well, root 2 times root 2 is 2. But look, the 2's cancel out. So this is actually square root of 2. So now, right, I would say it's clear that, the square root of 2, even though these are equivalent, I think we would all agree that the square root of 2 is better, right? That certainly looks better. This looks more complicated. We don't really know what that is, but when we start getting used to square roots, you would say, well, this is about 1.41. So, okay, so what else can we do with square roots? We can simplify another way. How about the square root of 50? So there's a property of square roots that says, well, if 50 is 25 times 2, I can now split that into 2 square roots. That's the same as root 25 times root 2. I think we've kind of been using that implicitly. But note that the square root of 25 is equal to simply 5, because 5 times 5 is 25. And so here what we have is root 50 is the same as 5 root 2. And again, and see in these two cases, the bottom ones are clearly more simplified. Why? Because you typically just with square roots, you want to pull out the whole numbers It's just, again, it allows for kind of more clarity as to what about it is. Like, again, if you know 2 is about 1.4, you can say, well, this is about 5 times 1.4. It gives you a better idea of what number it actually is. And it's just the norm. Okay, these are simplification norms, and you want to know how to do them. We'll do one more like this one. Let's say, I'll just put it over here. If you have like, what if I have the square root of 12? Now this is an interesting one. Why is it interesting? Because 12 you can write in different ways. I can write 12 times 1, 6 times 2, and 4 times 3. So if you simplify these to times 1, you know, that's not going to help you. Kind of like when you're looking at reduced fractions, you could say, oh, well, 1 goes into it, divide both by 1. You haven't really changed anything. So you can simply ignore that one. So how do I choose if I want to split to 6 times 2 or 4 times 3? Well, let's look at this one as an example. The reason why this was useful is because 25 is like a perfect square. So if I did like 6 and 2, just to show you, right, this is 6 and 2, neither of those are actually a perfect square, so I can't directly simplify one of them. See that? But if I change these and I say, hey, let me actually try 4 and 3, now I can say, that's better because square root of 4 is 2. Okay, and that's 2 root 3. And when you're transitioning from Pythagorean theorem to trigonometry, a part of that is you want to have mastery over square roots and understand how to both rationalize the denominator and to simplify square roots. Okay, we'll cover one final topic, and this is calculators. So here's the deal. We haven't yet introduced what I would call, it's radians, okay? Some of you may have heard of that, and we will. But let me put it like this. When you put in with the sine, okay, sine of 30, we had this before. The sine of 30 degrees is equal to 1/2. Degrees is really important, right? Because that's a unit. And there are different measurements. I should say there are different units. And radians is very common. So if you put in the sine of 30, okay, like you should try it on a calculator. Just try sine of 30, okay? Usually it's a function. You put it like that, actually. And then you can hit enter and you'll get some output. And the output is likely to be one of two things. Either 0.5, which is correct. Yay if you get that. Or something totally different. And if you get something totally different, it's because you're in radians. And so on calculators, because everybody uses both degrees and radians, you will see why later with radians. It's not a quick topic, but it's a very advantageous one once you get the hang of it. You got to learn how to go back and forth. All calculators are different, but I will tell you that there is an option, okay, if you look. And again, if you're getting sine of 30 equals 0.5, then you have the correct option, okay? But if you're getting something different, you want to switch it to degrees. So to start with, you want to use degrees, but the note is that you may need to change from radians, okay? And I will say this as well. One of the most common errors at this level is actually having it incorrectly on a calculator. Now, I just got through a bunch of examples where we didn't need a calculator. So when would you need a calculator? Let me show you. So if your angles are the following, okay? Now, eventually we'll cover more of these, but we didn't cover like 0, but let's just say 0, 30, 60, oops, I want 45 in there. So every time I hear 30, I think 30, 60, 90, okay? 30, 45, 60, 90, and multiples of those, no calculator, okay? We didn't cover 0 and 90, but you'll learn those soon. They're pretty straightforward. We covered the harder ones. Well, guess what? Everything else is a calculator. So if you're presented with the problem, okay, I'll write this up here. If you guys notice a little programming there, if else statement. So if angles in this, otherwise, I'll just say otherwise. Else, it's another way to write it. So otherwise, calculator. So for instance, if somebody says, hey, what's the sine of like 22 degrees? Guess what? I don't know. And you know why? Because you do that on a calculator. All right. And this gets into a really critical distinction with where we are in math curriculum today. And when I say today, I'm not just speaking about high school. Okay, I'm talking about college. I'm talking about not just like any college math and science, but at the highest levels, college math and science. You are expected to know these without a calculator. Okay, you just are. Often it's the case that you'll be expected to exams and quizzes in your future in which you will not receive a calculator, nor will you be permitted to use one. And you're going to need to know things like what's the tangent of 60 degrees and know how to generate it on your own. Okay. However, because we want to take the sine, cosine, and tangent of any given angle, you're also going to be using the calculator. And I think when you're first starting out, it's okay to use the calculator to check, right? You're like, well, I got 1/2. Is it really 1/2? Hey, put it in your calculator and check. All right. But do note this important distinction because you want to know what's expected of you, right? If I give you another one, like let's say cosine of 44 degrees. Well, that's close to 45. What do? Calculator, okay? These are calculators. Right? You just put it in. And what I'm saying is this. When you're using your calculator, you want to verify that it's actually giving you the right answers first by checking one that you know, like the sine of 30 is 0.5. Right? Because if you're in radians, and this is degrees, you're going to get the wrong answer. Okay? Radians are coming later. Okay, so that's a summary of a lot of different things. The fundamentals really on how to work on your transition from the Pythagorean theorem to trigonometry. Okay? There's a lot of stuff here. And I will say this too, it's a little disorienting the first time that you see it. For some of you, this is not your first go around, but you will actually get used to it. And you're going to see a lot of sine, cosine, and tangent going forward. These are going to become functions in their own right. And as I hinted at with things like solving polygons, which you could see at some point later, even like the first equality for the number pi, which you could also see in your future, or what you'll see a lot of this year really is just using sine, cosine, and tangent as functions that produce waves and all kinds of other interesting properties. This is the beginning of a really exciting discipline of study. And it doesn't require a ton of memorization, but it does require a little. And if you put the work in now, that little bit will go a long way. Thanks.